In an attempt to create an X-ray shader, I managed to create this really neat looking full screen effect. So in this video, I'm going to show you how I made this and how you can use it for your project. So to start off with, we're going to go to our assets folder, we're going to right click, we're going to go up to create, and we're going to find shaders, and then we're going to create a URP unlit shader. We're going to name this color cutout shader, and then we're going to press enter, and then we're going to right click it again and create a material based off of it, and we'll call this the color cutout material. And then the last thing that we're going to create here is we're also going to right click and create a mono behavior, and we're going to call this color cutout controller. And then open both of those up in Visual Studio. So this is the URP generated shader. We don't need everything in here, so we're going to remove both of these properties. And then in the pass, we're going to get rid of the texture 2D for the base map and the command buffer. Next, we need to modify a couple things. So in the varying section, we're going to change position HCS to just pause. It's easier that way. We can leave the rest the same. In our varyings, we're going to change that to be pause. And then we're also going to change a little bit of our attributes. So instead of having the float 4 and the float 2 for UV, we're going to change this to a uint. And we're going to name it vertex ID. And then we're going to inherit that from SV vertex ID. Next, we're going to change some stuff in our varyings. We're going to make the pause equal to get full screen triangle vertex position. And then we're going to feed it in the in.uv parameter. So add in the in.uv. Make sure you spell this correctly. I didn't here. For the second part, we're going to use get full screen triangle text coord instead. I did make another mistake here where it says in.uv. That should be in.vertex ID. It's corrected later on, but if you try to run this and it doesn't work, that's why. So next thing we're going to do is we're going to get rid of the code from our frag here, just because we don't need that there. And then we can actually start getting ready to do some stuff in our shader here. So I have another script that's already ready to go. I'm just going to copy and over a lot of these values here. So in our properties, I'm going to paste down our color values. So we have a near color and a far color. That header and space stuff up at the top is just to make it look pretty in the inspector. But those are our two colors. We're going to default the close to 1 and the far to 0. Then just above our attributes struct, we're going to redefine these because the properties only defines them on the CPU for the inspector to use. We still need to define them on the GPU within the pass. So I'm putting these in as half 4s instead of floats because a half 4 is half the precision and it's faster to compute with a half 4 and you really can't notice much of a difference. I'm also going to add 3 more properties here, one for our focus depth, another one for our edge threshold, and one for the fall off. These control how far away you look, what we determine as an edge, and how far it should fall off when we're doing the color cutout effect. Now, same as before, we need to declare them on the GPU. Now we can start actually doing something. So what we want to do with this shader is we're going to want to work with the depth texture. So we need to do an include. So what we can do is hashtag include, and then we're going to copy and paste everything up to shader library from the core HLSL package. Paste that, and then it's going to be / declare depth texture .HLSL. This allows us to access a bunch of helper functions for reading from the depth texture. So now we have to work on actually sampling the depth texture. So I'm going to copy some coding here. There are 2 ways to do this depending on the platform you're on. So it can be different per platform. So reverse Z is typical for DirectX and console as well as Windows applications, Microsoft products, but normal Z can work for mobile or certain other as well as some graphics processing systems. So we do if Unity reverse Z, then the depth is just the sample scene raw depth value from the sample scene depth. If it's not reversed Z, then we have to lerp from the near clip value to 1 based on the between the near clip value. So we're just flipping the value. So there are 3 ways to sample your scene depth. You can do raw, linear, or eye sampling. For raw sampling, the near clip plane is going to represent 1, and the far clip plane is going to represent 0. However, the distance between these isn't linear, it's exponential. So as you get further, the color drops off much more quickly. With linear scene depth, it's the exact same thing where 1 is the near clip plane and 0 is the far clip plane. However, this is a linear representation. So the intensity values drop linearly. With eye scene depth, it's giving you the actual distance in units. If you try to just render this, it will be extremely bright because the values will be greater than 1, so it'll think it's an HDR color. But it's giving you an actual readout of the number in units of how far away that point is. Now, before we actually work with the depth, we're also going to grab the blit texture. The blit texture is what the GPU is saying needs to be drawn on screen, so it's the full color version of what the camera sees. We're going to set this as a texture 2dx of underscore blit texture. This is a globally accessible texture in Unity, so you can just call this, you don't need to define it anywhere. We also need a sampler named sampler underscore the texture. It has to be the same. And then we're also going to get a half-2 of the blit texture underscore texel size. This is needed for doing our edge detection later on. So now let's actually do something. So just to start off with, what I'm going to do is I'm going to paste in some code here. And what this code is going to do is it's going to get the blit color by sampling that texture 2D at our UV coordinates. So we're setting this as a half-4 because it's easier to work with half-4s. So we're getting the RGB of it and then setting the alpha to 1. The next thing we're going to do is we're going to get the eye depth. So you have to put the raw depth we sampled in, and then we need to also feed it z-buffer params. This is required so it knows how far away it is. This is basically using the Unity inverse projection matrix to determine where the point is in space. Next, we're going to define our depth color. This is going to be another half-4 that lerps between the close tint and the far tint, and it uses the eye depth and then some math with the focus depth. So what this does is it means whatever our focus value is set to, that'll be right in between. It'll be evaluating the lerp at 0.5. One last thing we're also going to grab here is another half-2 of the texel size. We're not going to use it yet, but we're just going to grab it now. And then finally, just to test this out, what we're going to do is we're going to return the depth color. So if we do that, then save it and go back to Unity. And now we need to actually use this. So what we want to do is we want to go to our settings folder. Your project should automatically create one. I just moved the stuff over from the default one. In here, the part we want to get to is the PC render or whatever renderer you're using. We want to go add render feature, full screen pass render feature. We're going to rename this to color cutout feature. And then we're going to change the injection point to before post-processing. And then where the material is, we're just going to put in our material there. So now you can see we got this kind of depth effect going. And if I go into the material settings and I change the focus depth, you can see that's what that focal value was doing. It's changing where our line between what's close and what's far is. So by modifying that, you can change the effect. We're going to later on modify this at runtime. You can also change these colors so that way you have different colors for your near or far values. So as you change them, they'll update. Back in our shader, we're going to get rid of this return depth call. While that created a neat effect, that's not what we're looking for here. So we're going to remove that and we're going to add in our code for edge detection. So this is the Sobel method. This is some linear algebra I don't fully understand, but luckily Google does, so I just copied and pasted from it. But basically what we're doing is we're creating a kernel and sliding that along and seeing if there is a major gradient across the kernel. We do have to make sure we have two versions, one for reversed Z and one for non-reversed Z. And unfortunately, we can't just reuse our depth value because we're only taking that in at our main point, whereas here we need to take in the areas around that point. So we have to have this Unity reverse Z again, and it will pop up one more time later on. Next is putting in the actual Sobel operator. So we have an X component and a Y component, and then we get the magnitude by squaring each value, adding them together, and getting the square root of the two of them. So this is standard vector magnitude. And then we check if it's an edge by doing a step between our edge threshold and our magnitude. So a step returns either 0 or 1. This is basically a bool. And we check if it is or is not an edge. So just to see how we're doing, we're going to add in a quick return here just to evaluate how our shader is going, make sure everything's working properly. So what we're going to do is we're going to say if is edge. Luckily with HLSL, a int can behave as a bool. 1 is true, 0 is false. So if it's an edge, we're going to return the far tint. And then otherwise, what we're going to do is we're going to instead return our close tint value. So now, after we have those returns set up, we can save this and head back over to Unity and see what we have. So now, if you go and play with the edge threshold property, you'll see that you now have an outline around everything. What that property is doing is it is saying what the difference in the gradient needs to be across the kernel. So the higher the number, the larger the step needs to be, so we only notice large jumps in depth. The lower the number, the smaller the jump in depth for it to show. You start getting some artifacts with really low numbers. Next up is our volume detection. So this function here, it takes in a point in world space and it determines if it is inside one of the volumes we set. So we have a vector4 array that is our underscore volumes, and the first three values, the x, y, z, are going to be the center of our circular mass or our spherical mass, and then the w component is going to be the radius. P is the point in world space that the camera points to. So we're checking if this point is inside that space by measuring the distance. The math within the saturate as well as the times equals inside for the mask is so we can have our fall off or feathering around the edge of our volume, so it's not just a hard line between what is inside and what is outside. This pulls from a few new properties, so we need to declare those variables. So we have an int for volume count and a half for array for volumes. I set the max to 96 because it limits how much the work the GPU has to do. We also already have our fall off set. The reason why I set the volumes to 96 is because you can't modify this at runtime, so you need it to be big enough that it works, but not so big that it's going to completely kill your GPU trying to run this script. So now below our edge detection, we're going to add in a function that gets the world space position. So half3 world pause is equal to compute world space position. We're taking the pixel point, we need our depth value, and we need the inverse projection matrix. And then what we're doing is we're taking that value and we're feeding it into our volume mask to get our total mask. So this is a value between 0 and 1 of how much it is either inside or outside a volume. Then we're going to define another half4, and this is going to be our lerp end color. Don't accidentally have two equal signs. I spent a while trying to figure out why this wasn't working. It should just be half4 lerp end color equals far tint, not half4 equals lerp end color equals far tint. But now in our is edge, we're going to say lerp end color equals depth color. And then beneath that, what we're going to do is we're going to return a lerp, and this lerp is going to go between the close color and then our lerp end color is the end. And what we're going to use as our t value is going to be our mask. So that way it's changing depending whether or not it's inside or outside one of those volumes. So now if we save this and we go back into Unity, what you'll see is now there is the outline shader. And what we need to do is we need to actually define our volumes. To do this, we're going to jump over to our color cutout controller mono behavior that we made at the beginning. And what we're going to do is we're going to add a public material, and this is going to be our cutout material. And then what we're also going to add is a public static int, and that's going to be the maximum amount of volumes we're allowed to have. The reason why this is static is because it's easier not being an instance variable in this case, and it makes it so you can modify it at runtime. So this would be how you change things like graphics settings to be, low or high quality. You'd change that number. We're also going to make a public struct called color volume, and this is going to have a public vector 3 in it that's going to be the center. So this is the XYZ components we were getting in our shader, and then a public float for the radius. Then we're going to add a public color volume array, and this array we're going to initialize it to the same size as our max color volumes. And then from there, what we're going to do is we're going to go into the update loop. We need to add a tag here that is execute always. This isn't something you always want to do. This is making it run in the editor without play mode being on and in play mode. If there are errors, it will be a nightmare because it'll just throw errors nonstop every frame, even when you're out of play mode. So you need to have some way of preventing those errors. So we're just going to have an if cutout material is not equal to null before we do anything in the update loop. This just makes it so if that material is not set, it won't do anything. So first thing we're going to do is we're going to define an int called count, and this is going to be equal to mathf.minimum of either our volumes.length or our maximum color volumes. So this lets you make the volumes array bigger, but it'll only ever pass whatever your maximum number is. So then what we're going to do is we're going to get our material and we're going to set int, and we need to use, in quotes, the exact name we defined it as. So this one is volume count, and then we pass it whatever int we want, in this case count. Then what we're going to do is we're going to define a vector4 array, and this is going to be just our v array, and we're going to initialize this as a new vector4 array of size count. Then we're going to make a for loop here, and we're going to go through this for loop for I equals 0, I must be less than count, I plus plus. Once we have that, inside that for loop, this is where we're setting those vector4 values to be our x, y, and z components. So v array at I equals new vector4. So our x component is going to be our volumes at I dot center dot x. Our y component is going to be volumes at I dot center dot y. And then, as you probably guessed it, our z component is going to be volumes at I dot center dot z. Our w component is going to be volumes at I dot radius. So we're just passing this into a single struct rather than having them be two separate things. Then the last thing we need to do here is we need to set our array. So we get our material and we set vector array, and we need to, again, make sure in quotes we spell it exactly properly. So underscore volumes, and then we're going to pass it the vector array. So with this set, we should, for testing, make sure to add the system.serializable flag to our color volume struct. This just makes it so we can see it in the inspector. Next, we're going to put this script into our project, and we're going to drag in our material. And if we just select element 0 here, and we make its radius something like 10, now we have this blob of blue here. So inside that volume, it's saying, okay, I should be the other color that we set. We're going to do more with this later on, but right now this is just a test to say, okay, our volume detection is working. So now back in our shader, if we go and we replace close tint with the blit color that we pulled earlier, now what it'll do is instead of being that blue, it'll go to the camera blit texture. So if we go back here, what you'll see is now you're actually seeing the color. It looks like what it would look like with just a normal camera. So that's how we create our color cutout. If you adjust the fall off, you can see it's creating that different effect. We can move it around, change the radius. So you can set these in script at runtime to be whatever you want, or they can be static and stay still in the scene. It's up to you. We're almost there. Now it's just time to add the last part of our shader file, and this is going to be our noise. So I pasted a bunch of properties here for noise scale, octaves, linearity, persistence, as well as whether or not we want to use it for outside of the volumes, if we want to use it inside the volumes, or if we want to use it on the skybox. I am also going to add another parameter up here, and that's going to be a show skybox. So if it has the flag material toggle, it behaves like a bool, even though it's set as a float. This means whether or not we'll show the skybox through the effect or not. So next we need to actually make our Perlin noise. Again, Google was wonderfully helpful for this. I don't understand all the math entirely, but what we're going to do is we're going to define a function for creating a hash. Again, I'm using halves here just because halves, it really doesn't matter. We're not getting the precision we need out of a float, so it should be fine with just halves. And then we're going to add in another function. This one is going to be for the actual Perlin noise. This is technically doing it in 3D, but we're only actually using the 2D component. It's just the formula it gave me was for 3D. So we still use a 3D formula. And then we need to add one more function here, which is going to be our actual Perlin noise, what applies the 2D noise. So it feeds in a point and we multiply the UV by the noise scale and set the Z component to 0. And then one last one, that's layering it. So this is so we can create multiple layers over top of each other so it doesn't look quite as much like typical noise. The more layers you have, generally the better. So we do need to actually define our values on the GPU that we're going to use for our noise functions. So we have all of our noise properties as well as our min-maxes. I accidentally made the noise octaves a bool in the video. Make sure that is set to a half or else this will not work. The noise will never scale properly. Now we just got to put the last little bit of this together. So first we're going to do the skybox. The skybox will always be past the camera's far clip plane, so it'll always return the maximum depth value. So if it's reversed Z, that's 1. If it's not reversed Z, it's 0. So we check that. And then these functions here, so we want to make sure that we are checking if it's furthest and we have show skybox enabled. And then there's also another if of use noise on skybox. So if not, we just return the blit. If we do use the noise on the skybox, then we have a lerp here where we multiply the blit by another lerp between the minimum, maximum by the Perlin noise, because the Perlin noise is always between 0 and 1, so we can use that lerp to refine what our 0 and 1 values are. We're doing the same thing for the reverse C, except it's set to 0. Okay, so that's the skybox. So now if we go back down to the bottom here, we just need to add in a couple more things to get this shader fully working. So next we want to add another if, and this is if use noise inside volumes. Then we want to multiply the blit color by the inside noise min max lerp. If we want to use the noise outside the volumes, then we want to, instead of doing the blit color, we want to do the lerp end color and multiply that by the outside min max lerp. And then finally, we can just return the same thing. Now, if we go back to Unity, what we have is we have our shader working. We have a noise texture being applied over everything at the moment because all 3 of the bools are checked. But if we play around with some of the different noise values, we can change that noise. It's applied in a screen-wise way because the texture we're getting is the screen coordinate. So it applies directly on the screen. I think it looks neat for creating kind of a paper effect, but I'm not entirely sure how you'd apply it to a surface. That would require some more thinking that I don't think I have in me for today. But we can adjust all these different stuff. If I click show skybox, now the skybox is hidden and instead we're not seeing it. And again, if I adjust the depth, that's changing now how far we're seeing the outline. So the focus depth now affects the outline. If I change our volume fall off, you see the difference. If you make the fall off greater than the size of the volume, it'll just have a hard line. So I'd recommend making it smaller than the size of your smallest volume. And then if I uncheck our noise here, you can see the noise isn't on, and now it is. I can uncheck it for the areas where we're just showing the blit color, and I can also uncheck it for the skybox. It's a little hard to see, so if I just quickly adjust my light direction so it's daytime, and then now I go back and I check the skybox, you can see it's applying this noise texture to the skybox as well. So you can really adjust this however you want to create the effect you're looking for. These are definitely not the best colors to use this for. I was just going with these 2 for emphasis, but I tried to make it as easy to use as possible with as many different parameters so you can adjust this to whatever you need. Now we just need to go back to our controller so we can add a few little features to it to make this depth even better. So back in our controller script here, we're going to define some new variables. We're going to get a public float. This float is going to be our smooth speed. So this is going to control how fast the focus comes in or out. We're going to set another public float, and that's going to be our max focal distance. So I did also off-screen set a minimum focus distance, and in the scripts I'm going to share, it'll be in there, so you can just use that. Then we're also going to make a private float for our previous depth. And the last thing we're going to make is another public transform this time, and this is going to be our camera transform. To determine what our focus depth is going to be, we need to raycast out from the camera, so we need access to its transform so we know where it is and what the forward direction is. So next we're going to go down to the update loop, and we're actually going to put in our raycast. So we want to define a raycast hit, and we're just going to call it hit. And then after this hit, what we're going to do is we're going to define a float. This float is going to be our focus distance. So we're going to default it to the maximum focus distance. So that way, if for some reason the raycast doesn't return, it'll just say, okay, I should set to the max focus distance. And then if physics.raycast, and then from that raycast, we need to send out a ray from our camera transform.position in the direction of the camera transform.forward. Spell forward right, and it'll actually work. And then we want to out our hit, And then we also need to add in here that we want the max distance to be our max focus distance. So that way it doesn't try sending a ray out to infinity. It just somewhat very, very minorly helps with performance. So spell forward correctly. And then within this, what we're going to do is we're just going to set our focus distance equal to the hit.distance. So it's that easy. We just get the distance between the camera and the hit. So now what we're doing is we're going to write a smoothing function here. So we're saying focus distance plus previous depth times our smooth speed. So all of that in brackets divided by the smooth speed plus 1. It's a bit of an annoying function, but basically this means that the higher your smooth speed, the longer it takes, the more it weights the previous depth over the current. So the steps it takes between it is larger. Then we set the previous depth equal to the current distance. And our material, we set the float underscore focus depth. And we set that as our focus distance. So now we have that set there. So make sure you set your camera as the transform in the script. And then now once I go into play mode here, just give it a second. And I actually look somewhere. So now you can see as I look at things close to me, the outlines tend to fade, whereas when I look far away, they appear. So you can adjust this effect. You can make it so it's the background that fades instead of the foreground. Play around with it in the shader. It's quite easy to do, but that's really all there is to the focus depth. And the last thing, the very last thing we're going to add is going to be a dynamic depth of field. So we need to get a public volume profile. This is going to be our post-processing profile that we use. In this video, I just use the global one that's by default in URP. Then we also need a public depth of field component, and this I'm just going to name DOF. And then what we want to do is we want to go into our update loop here, and we're just going to kind of shove it wherever it fits. And if DOF is not null, then what we want to do is we want to set the start and end of our Gaussian blur. So we want to get DOF Gaussian start, and we want to set it equal to the focus distance. And this case, we're going to do focus distance minus focus distance over 2. This just means that it's going to blur what's half of the focus distance away, and it's going to start to blur what's half of the focus distance before. So we want to make sure we also add the dot value there. Don't forget that. So for the start, we're doing minus the focus distance, and for the end, we're doing plus the focus distance. So that way we have that buffer space where everything is in focus that we're actually looking at. So with that, that should be the actual setting of it. We still need to grab the depth of field component. So in start, we just want to add volume.tryGet, and then we want to make the type a depth of field. And then in the parentheses, we're going to out our DOF value. So on start, this will try to get out our DOF value. And then once we go back to Unity and actually reload it here, you'll probably have to go into play mode the first time for it to set, so it'll update while you're in edit mode, just because you can't easily drag it over from the volume profile component. But once you press play, it should automatically set itself there. And then once you have that set, everything should work. Now, if you go into play mode, there's just a bit of a subtle blur effect when things are either far away or really close and they're not in focus. So I played around with some different colors, some different noise settings, and this is what I was able to make. If you like, please let me know. I'd be happy to make more shader videos. This was just a neat thing that kind of popped up while I was working on something else. And yeah, thank you for watching.